Training teaches an AI model once. Inference runs it billions of times. Training is an offline, compute-heavy factory that optimizes weights with massive parallel backpropagation. But deployed inference is online, real-time, and user-facing, choked far more by GPU memory bandwidth and allocation fragmentation than raw compute flops. Today we break down high-performance LLM serving, Prefill versus Decode, KV caching, PagedAttention, continuous batching, and quantization. Every LLM request runs in two fundamentally different phases. The prefill phase takes the entire prompt and processes all input tokens in parallel with matrix operations, saturating your GPU's tensor cores. The decode phase then generates token by token, autoregressively. To emit one token, the GPU must fetch billions of weights and past context from VRAM into local SRAM, doing matrix vector math with near zero arithmetic intensity. So your GPU spends 90% of its clock cycles idle waiting on the memory bus. Naive autoregression would recompute attention keys and values for every past token, giving quadratic time complexity. Engines instead compute key and value tensors once and cache them in GPU memory, but the KV cache is massive and expands with every generated token. For a 70 billion parameter model serving 50 concurrent users at 4,000 context tokens, the cache alone likely exceeds the memory footprint of the model weights. Early serving frameworks pre-allocated contiguous memory for each user's maximum context length, wasting up to 80% of VRAM to fragmentation. PagedAttention, pioneered by vLLM, breaks the KV cache into fixed-size physical blocks, 16 or 32 tokens per page. A page table maps logical context to non-contiguous physical memory on the GPU. This cuts memory waste below 4% and boosts concurrency 2 to 4 times on identical hardware. Static batching stalls the entire GPU until the slowest request finishes. If one user generates 500 tokens while another generates 5, the fast request is blocked. Modern engines use continuous batching, or iteration-level scheduling. The scheduler steps every request forward one token at a time. The instant a request emits an end-of-sequence token, its pages free up and a new request joins the next iteration without missing a beat. Decoding is memory bandwidth bound, so shrinking weight precision accelerates tokens directly. Converting 16-bit weights to 8-bit cuts memory in half with minimal quality loss. 4-bit AWQ or GPTQ cuts it 4 times, letting a 70 billion model run on a single GPU. Then flash attention accelerates attention by tiling matrix math into fast SRAM, and never materializes the full n-by-n attention matrix in slow VRAM. Traditional response time fails for LLM SLAs. Track time to first token, how fast the first streaming character appears, driven by prefill and queue weight. Track intertoken latency, which feels instant under 30 milliseconds. Add total tokens per second across the cluster, and KV cache utilization, because when it hits 100%, requests queue up and time to first token spikes exponentially. For high concurrency cloud fleets, standardize on modern engines like vLLM, TensorRT-LLM, or Hugging Face TGI, paired with quantization, continuous batching, and flash attention to maximize tokens per dollar. For edge or cost-constrained private deployments, use llama.cpp with GGUF quantization on commodity hardware, and always stream tokens over server-sent events. Never make users wait for full generation to complete. In summary, training builds the engine, and inference drives the car in production traffic. Master the split between prefill and decode. Eliminate memory fragmentation with PagedAttention and head-of-line blocking with continuous batching. Accelerate the memory bus with quantization, and stream every single token. High-throughput inference turns bleeding-edge models into profitable, low-latency products. This is day 19. Tomorrow on day 20, AI agents versus chatbots.